So the simplistic version of explaining how an enzyme works is this whole lock and key model. The idea that the substrate has a shape that's complementary to the active site. It binds, products are formed, or products could be broken apart or fused together, and then products are released. That's called the lock and key model. It's actually a little bit more complicated than that, and we have an explanation for what's called the induced fit model. The induced fit model works like this. When the substrate binds to the enzyme then, because of that binding, changes shape slightly so that it can perform the required action. That may be breaking bonds, that may be forming bonds. Once it makes that change and forms the bonds or breaks the bonds, it releases its products. After it releases its products, because there's no longer the interaction between the substrate and the enzyme returns back to its normal shape, and now it's able to catalyze a new reaction again. So here's a model that shows how the induced fit works. The enzyme is here. The substrate has about the same shape. It's drawn into the enzyme, which then changes shape because of the interaction with the enzyme, breaks it into products, releases products, and after the products get released, it returns back to its original shape. Let's look at it one more time. Substrate is pulled in, binds to the enzyme changes shape. Because of that, enzyme releases products and returns back to its original shape. So that's the induced fit hypothesis. Now, what do enzymes actually do? Well, first, in your body, here's one specific example. Every reaction in your body is run by enzymes at a speed, a rate that's going to be fast enough to keep you alive. Inside your body, as you do cell respiration, you release lots of carbon dioxide. Carbon dioxide goes into the blood, but it doesn't dissolve in the blood. It could build up as a gas. There's a normal chemical reaction that occurs with carbon dioxide and water, and they react and produce carbonic acid. So rainfall doesn't have a pH of 7 because it's not pure water. It reacts with the carbon dioxide in the air, and it produces some carbonic acid in the rainfall. So rainfall normally has a pH of about 5.6 or so, slightly acidic. Carbonic acid is soluble in the water, in the blood. So that's how it gets transported back to the lungs, and then it gets converted back to carbon dioxide. If you left this reaction by itself, though, it would be much, much too slow to remove enough carbon dioxide. We would probably die from a buildup of gases in our blood. Luckily for us, we have this enzyme called carbonic anhydrase, which speeds that reaction up so that instantaneously, 10 million times faster than normal, as soon as the carbon dioxide hits the blood, boom, it's turned into carbonic acid, goes through the bloodstream because it's soluble, gets to the lungs, boom, it gets turned back and we breathe it out. So that's one example of where enzymes actually keep us alive just by about what's going on in our blood. Enzyme action is extremely sensitive to environmental conditions. We've talked about that before. We talked about the high temperatures, that they could change the shape of the active site. They could denature the enzyme, melt them. We talked about pH outside of the normal range, whatever the normal range is for that enzyme, that it could change the shape of the enzymes. But sometimes other chemicals can also have an effect as long as they're changing the shape of the enzyme. Two examples on what kind of an effect they could have. One is coenzymes. Co means together, so these things work together with enzymes. And the way they work is that they bind to an enzyme and they actually help it to function. There's a couple different types, but here's one specific example. Let's say you had an enzyme with this particular shape. Okay, a coenzyme might be necessary to bind to the active site, and it will actually change the shape of the active site with that binding to create a functional active site for the substrate that it needs. So this enzyme by itself wouldn't work until a coenzyme binds to it, and that changes the shape. There may be other coenzymes which bind to other parts of the enzyme and then, in effect, change the shape of the active site or make it work faster. Okay, so that's what coenzymes do. They help enzymes work better. It's important to eat your vitamins because many of them act as coenzymes. The other side of the coin is that some of them inhibit or prevent enzymes from doing their job. Enzyme inhibitors are similar to coenzymes in that they bind to an enzyme, but they actually change the shape of the active site in a bad way. There's a couple different types of those, but some examples. Tamiflu is an antiviral medication that they give people for the flu now. It's an enzyme inhibitor. It blocks the active site of viral enzymes so that the viruses aren't able to replicate themselves. If you can't kill the virus because it's not alive, what do? You block it from actually being able to make more viruses and inhibit the enzymes. Cyanide is a poison. We know that it kills people, but why? Because it inhibits enzymes that run cell respiration. So it actually blocks those enzymes from working, and that's what kills you. Here's an example of what it looks like. Here's a normal enzyme. It has a substrate that fits perfectly into the active site, and so that's how it would work. If you had a competitive inhibitor, that means that it's going to bind right to the active site and block it so that the substrate can't fit. If you had a non-competitive inhibitor, it would bind to the opposite side, a different area on the enzyme, which would then alter the shape of the active site because of the interactions of hydrogen bonds and so on, so that the substrate can't fit into the active site, and then the enzyme wouldn't work. This is what's called an allosteric interaction, where when something binds to a large molecule and then changes the shape of that molecule, in this case this would be an allosteric enzyme inhibitor, because you're not blocking the active site, but you're changing the way it's going to work and the shape of it. Other examples of how enzymes are used, other than just inside of our body, they are used to make cheese. I went to a cheese factory one time many years ago up in Vermont, and the process has changed a lot, but they used to just put milk out in warm trays and let it ferment, and they would let bacteria work on this cheese until it curdled the milk and turned it into cheese. They started to look at this, and scientists said, I bet you we can speed this process up a lot. And they figured out that what is it that the bacteria are doing? They're using an enzyme called renalase, and they're using it to turn the milk proteins into cheese. So they figured out if they set up an industrial vat at the right temperature and they add renalase enzyme, they can speed that right up and they can make cheese. You can actually buy cheese-making ingredients and do it yourself at home. Depending on the spices and salts and things that they add to it, that gives it different flavors. What else? Beano is a pill that you can take to prevent gas. Their slogan is, take Beano and there'll be no gas. The idea behind it is when we eat lots of vegetables and beans and things like that, they have complex carbohydrates in them called oligosaccharides. Human beings don't have the enzyme, which is called alpha-galactosidase enzyme, to break down those carbohydrates. So they go straight through our small intestine without us digesting them. They get to our large intestine where they encounter E. coli bacteria. E. coli have that enzyme. So they digest these oligosaccharides, they break them up into sugars, and they digest them, and as a byproduct they produce sulfurous and methane gases, which provide uncomfortable moments in public for you. The idea now is, take Beano before you eat these things. It is alpha-galactosidase enzyme in a pill. That enzyme will be in your small intestine when you eat those foods, so you'll be able to digest it, and the bacteria won't get to eat it. Another option, another enzyme is lactase. This is lactase enzyme in a pill for people who don't have the lactase enzyme in their body or don't produce it enough, so they would get indigestion and upset stomach when they eat dairy products that have a lot of lactose sugar in it. Meat tenderizer is an enzyme. My father-in-law used to marinate his steak in pineapple. He'd crush it up and put it on there, and he'd say, oh yeah, it makes it really soft. Well, he's right, because pineapple is the source of the enzyme papain, which they isolated and made it into a powder so you could sprinkle this on a piece of steak and it will tenderize the meat. There are lots of detergents now that use enzymes. For instance, for archery hunters, Dead Downwind is a whole line of products that digest the molecules that produce human odor. And there's other laundry detergents as well. So they break down and get rid of certain molecules that produce scent and dirt and things like that. So you'll see lots of enzymes showing up on detergents that you might buy at the store. Lastly, did you ever have a chocolate-covered cherry? If you have, did you ever wonder how they get the cherry and all the syrupy goodness inside that thin chocolate shell? They can't eject it because it's a big cherry. What they do is they take this cherry, they roll it in an enzyme called invertase, then they coat it in chocolate. And then inside the chocolate shell The enzyme digests the cherry and turns it all into sucrose. Go have one, they're yummy.